Hello? Hello? Okay, so if you can hear me, kindly make a comment on the comment section. Okay, so if you can hear me, kindly make a comment. Okay, okay, let's see if we can actually wait to have more people online. We have just 7 persons online. Can you hear me? Okay. Okay, so let's do a quick review. So we can use the opportunity to wait for others to come online. And in our previous online lecture, we talked about triacylglycerol, where you have the glycerol backbone and fatty acid esterified to the glycerol backbone. Okay, let's see if we can actually wait. So if you have one fatty acid esterified, we have monoacyl glycerol. If we have two fatty acid esterified, we have diacyl glycerol. If you have three fatty acid esterified, we have the triacyl glycerol. We also talked about the nature of the fatty acids. Well, we mentioned the palmitic acid, the myristic acid, the stearic acid, the oleic acid, the linoleic acid. We also talked about the omega-3 and omega-6 and even omega-9 fatty acid. So we also talk about the monounsaturated fatty acid, talk about the polyunsaturated fatty acid and their implication in cardiovascular health. Now, this is a fatty acid composition of dietary lipids. So we have the source for beef. You have more of lauric and myristic acid. We have 5% lauric and myristic acid. We have about 24 to 32% palmitic acid. Stearic acid, we have about percentage 20 to 25. Oleic acid have about 37 to 43. Then linoleic acid, we have just 2 to 3. So beef is majorly from the source. This is data from Merck Index, 10th edition. So this is Principles of Nutrition, 4th edition, New York, Wiley. So in this document, we have the beef. If you look at the myristic, lauric, palmitic, stearic, and oleic acid are majorly saturated fatty acid. So that means beef have more of saturated fatty acids. Then we have the milk, which is majorly palmitic acid and oleic acid being in abundance. We have the coconut, which is majorly lauric and myristic acid, short chain fatty acid. Usually the short chain, this is lauric is 12, myristic is 14. So that's the total number of carbon atoms in this fatty acids. We also have the corn. We have about 34 to 62% linoleic acid. Linoleic acid is one of the essential fatty acids. We have for olive. Olive is only made up of oleic acid. Oleic acid. So now even palm, you can see that palm has more of the palm oil, have more of palmitic acid. Have more of palmitic acid. We have the safflower, which is 78% linoleic acid. Linoleic acid. So we have So we have different, we have the soybean. In fact, okay, there is this, I went to a supermarket to buy soybean, soy milk, you know. I was seeing on the label that soybean does not contain fatty acid. I just laughed. I decided not to buy again. How can you tell me that there's no fatty acid in soybean milk or soy milk? Yeah, I didn't buy again. I was like, no, no, no. That means the person did not do a proper nutritional evaluation of the product. So I can't trust what the person is selling. So we have the sunflower oil, which is majorly of linoleic acid. Like I said, the linoleic acid is actually one of the essential fatty acid. One of the essential fatty acids that is required for growth and development. So this is just a preview of fatty acid composition in this product that we encounter in our daily lives. So let me, based on our previous class, we're talking about triacylglycerol. Usually when we talk about biochemistry, we talk about this lipids, carbohydrates, amino acid, proteins, nucleic acid. We usually want to go take a deeper look on the implication of these things on different animals. Wherever the animal, wherever we can find the animal, their ecological niche, where their location in their ecosystem gives a direct implication of their biochemistry. And this is polar bear, which is known to stay in the Arctic region. Now, this polar bear hibernates for almost 8 months or more. They go into hibernation. That means they just have, out of 1 year, remaining 4 months. You minus 8 from 12 months. They have approximately 4 months. It's just have 4 months. So this 4 months is what they use to feed. And what is the nature of their feed? The polar bear is magnificently adapted to thrive in the harsh Arctic environment. Research by Malcolm Ramsey at the University of Saskatchewan in Canada and others, that is a team of researchers, has shown that polar bears gorge only during a few weeks out of the year and then fast for a period of 8 months or more, consuming no food or water during that time. The other polar bears feed almost exclusively on seal blubber, which is largely composed of triacylglycerol. You see that the nature of their food is to sustain them throughout the remaining 8 months. So they use the remaining 4 months to feed on this organism, the seal blubber. So which this seal blubber contains more of triacylglycerol. Now, why did they store their energy in triacylglycerol? Why did they store their energy? Why not proteins, or why not carbohydrates? Now, thus building up its own triacylglycerol reserve. Through the Arctic summer, the polar bear maintains normal physical activity, roaming over a long distance, relying almost entirely on its body fat for sustenance, burning as much as 1 kilogram to 1.5 kilogram of body fats per day. It neither urinates nor defecates, so it doesn't go to the toilet, it doesn't even urinate for extended period. Now, all of the water needed to sustain life is provided from the metabolism of triacylglycerol, because oxidation of fatty acid yields carbon dioxide and water. Now, for those, because if we are in 200 level, for those of you that are above 200 or up to 300 to 400, attending this lecture. If you're in biochemistry and you're 300 or 400, even though if you're in health science, medicine, and the rest, you must have heard about the electron transport chain and the oxidative phosphorylation. So the triacylglycerol is first of all mobilized. We have the sensitive lipases that will break down the triacylglycerol to glycerol and free fatty acids. The free fatty acids undergo beta oxidation. Now, this oxidation breaks down this fatty acid into acetyl-CoA, FADH, and FADH2 and NADH. The FADH2 and NADH are substrates for the electron transport chain and oxidative phosphorylation. So in that electron transport oxidative phosphorylation, that is where the water is produced as a complex 4. Where the CO2 is produced is at the TCA cycle. Remember, the acetyl-CoA that is produced as a result of beta oxidation enters the TCA cycle, where it is decarboxylated via a cycle of reaction, giving CO2. In fact, the step that involved that is just the conversion of isocitrate to alpha ketoglutarate, and from alpha ketoglutarate to succinyl-CoA. So that is the point where the CO2 is being produced. So the water that they use comes from the electron transport chain of oxidative phosphorylation, while the CO2 that's liberated as a result of the breakdown of the fatty acid is released in the TCA cycle. So this is, you can see that they are the region, and that 8 mode, they use that even for hibernation. That means no activity. They sleep throughout for 8 months. So as they are sleeping for 8 months, you can imagine how they're surviving. They are surviving because of their triacylglycerol reserve. So this is actually one of a take home. Now, we'll be looking at, after the whole introduction to lipids, fatty acids, triacylglycerol, our next topic is phospholipids. Now, these phospholipids are a group of molecules, usually we use, whenever we have one SI molecule, one SI glycerol, which is the monoSI glycerol, attached to a phosphate group. And the glycerol is also attached to a phosphate group. We refer to that as a phospholipids. Now, the phospholipid is made up of a glycerol backbone, 2 fatty acids esterified, and 1 phosphate group. So without any other thing attached to the phosphate group, this molecule you're seeing here is called phosphatidic acid. It's called phosphatidic acid. This is what makes it phospholipid. So it's made up of 2 fatty acid chains and 1 phosphate head. The phosphate head you're seeing here makes this molecule amphipathic. Amphipathic, like from the word amphibian, amphipathic. That means have both water-loving and water-hating properties. But I'm amphipathic. So it is a phosphate group that gives that character. So now the fatty acid chains, which is the non-polar, this chain is a non-polar part of the molecule. So you can see on this chain, you can see a structure that looks like the head, which is the phospholipid, which is the phosphate, and 2 tail, which is the 2 fatty acid. So that is how you'll see the fatty acid, this phospholipid, be represented in plasma membrane. And it's a major component of plasma membranes. It's a major component of plasma membranes because of this, the amphipathic properties that allows it to interact with water and also non-water molecules. So now we have these different phospholipids that are found in biological membrane. These phospholipids are found in biological membranes. Can we hear me? Joker, you're complaining you can't see what clearly. Let me just give me a hint of what you can see clearly. So I'll also say something concerning polyunsaturated and monounsaturated fatty acids. But let me quickly go through the phospholipids. So I've talked about the phospholipid, which is made up of a backbone, the phosphatidic acid. Now, this phosphatidic acid, you can see it here. You can see the nature of the molecule. This is one of the tail. This is another tail, and this is the head. So if you join it together, it now looks like this: one head, two tail. So if you're looking at the plasma membrane will have something like this. Let me just give yes, this is a typical scenario of a plasma membrane. You can see that head, you can see the head here. So this head is that phosphate group that is attached to an alcohol. I will name the alcohol that I found that are attached to that phosphate head. So you can see the hydrophilic head, the hydrophobic tail. You can see the two tail, which is those two fatty acid. So those, because of the nature of this phospholipid, they can form bilayers. And that is why they are used for biological membrane. And there is studies that have shown, okay, the fatty acid structure and the nodes. Okay, I will explain, I will give you more on the fatty acid structure. So you can see, based on this, you can see what I just did earlier. This is the head, as you can see here. This is the tail, one of the tail. The other tail usually like have a kink. The other tail is usually made up of a cis double bond. Call it a cis double bond. It will form what is called a kink. K-I-N-K, K-I-N-K, kink. So you can see the kink. It will look like this. One will be straight, the other one will be K-leg, just like someone that has a knock knee. So that's just the explanation. And there is a reason for this. That's why we say God is very wonderful. There is a reason for this. Now, Singer and Nicholson proposed the model, which is called the fluid mosaic model of the membrane. The fluid mosaic model of the membrane. So this kink nature will not allow the membrane to pack very well. Will not allow the molecule to pack very well, so that the membrane will look like a fluid. The membrane will look like a fluid. But if the membrane is very packed and rigid, it will be very difficult for molecules to pass through and out of the membrane. So the membrane must act like a fluid. That's why I call it a fluid mosaic model proposed by Singer and Nicholson. So these fatty acids are fatty acids that are attached, these are alcohols. This is an alcohol. You can see there's OH here. This is an alcohol called choline. You've heard about acetylcholine. This is the molecule that makes up acetylcholine. Acetyl group and the choline makes up to have acetylcholine, which is a neurotransmitter. This molecule you're seeing here is also another alcohol called ethanolamine. It's an alcohol, so it has a OH group, ethanolamine. This one here, cardiolipine, is a phospholipid that is typically found in heart muscles. So we have the phosphatidylcholine, phosphatidylethanolamine. We have this phosphatidylserine, where serine is the alcohol group that is found attached to the phosphate group. So we have something like this. Let me create a we have something like this. So we have something like this. This is the glycerol. Joker, pay attention to this so that you can see it clearly. This is the glycerol. Remember, this one is attached to a carbon. This is the first fatty acid. This is the second carbon. This is the second fatty acid. Now, this one should also have a fatty acid, but no, this time it is replaced by a phosphate group. So this is called a phosphatidic acid. Remember, there's usually a hydrogen here. Make sure you complete your hydrogen. So this is called a phosphatidic acid. It's called phosphatidic acid or phosphatidate. Now, this is the molecule that is found in biological memory. This is the first leg, this is the second leg. But usually the second leg is usually made up of an unsaturated fatty acid that has a cis type of double bond. A cis is that those kind of bond that looks like this. Let me give you something. So if the bond is like this, it's a cis bond. If the bond is like this, it's a trans double bond. The trans double bond. So what we have here, if now this oxygen here is attached to an alcohol like ethanolamine, you have CH2, CH, then you have NH3 plus. This is ethanolamine. So the same thing we have with this ethanolamine. The same thing we have with choline. Same thing we have with choline. So for choline, we'll have just almost the same thing. For choline, we now have N plus, then we have bracket CH3, 3. So this CH3 means that this nitrogen now has 3 CH group. 3 CH group. So it will look like this. To look like this, 1 CH3, 1 CH3, 1 CH3. So this is called phosphatidylcholine. It's called phosphatidylcholine. Now, remember I told you about acetylcholine. This choline is written as OH, CH2, CH2, N plus CH3, CH3, CH3. So this is called a choline, CHOLINE. It's called a choline. It's called a choline. So now, if an acetyl group is CH3, COO minus, which is an example, a kind of acetate. This is an acetate, which is a carboxylic molecule or an organic acid. If this acetylcholine reacts with this, is to remove the hydrogen and remove OH from here. We have CH3. So we now have a double bond to oxygen. So this is acetylcholine, which is a neurotransmitter. So from this, we can also have We can also have this is serine. This is serine. Serine is an amino acid. Let's assume this is our let's assume this is our phosphate group. This is our phosphate group. We have C for serine. Remember, C NH NH3 COO minus hydrogen is CH2. I don't know what's wrong with this. The pen is no longer writing. I think so. We have this is a serine attached to a phosphate group of the phosphatidic acid. So this is phosphatidyserine. We also have phosphatidyethanolamine. The diphosphatidyglycerol, which is known as the cardiolipine, which is known as the cardiolipine, which is known as the cardiolipine. The cardiolipine now is 2-glycerol. The glycerol, 2-phosphatidic acid, 2-phosphatidic acid joined together to another glycerol. You can see this is one of the this is the fatty acid. This is a phosphate group of 1 phosphatidic acid. This is another one with its own phosphatidic acid. Now, these two are now joined together by another glycerol. This is a glycerol. That we call it diphosphatidyglycerol. So this is phosphatidic acid. This is phosphatidic acid. So 2 phosphatidic acid means diphosphatidy. Then the parent here now is now glycerol. So diphosphatidyglycerol, which is called cardiolipine, is a major phospholipid that is found in the heart. So God is wonderful. There's a reason for all these things. There's a reason for all these things. Now, we know by empirical analysis, that the presence of these phospholipids gives a direct implication about the nature of the plasma membrane. The nature of the plasma membrane. That is why we know that these phospholipids are found in different proportions in different biological membranes. Now, the implication of this is that we say the plasma membrane is selectively permeable, allowing some molecules to flow in and out, while disallowing other molecules. Now, why is the membrane have that capacity? That is why what your heart muscles might allow, your liver might not allow it to pass. What the liver might allow, your kidney might not allow. What your kidney might allow, your pancreas might not allow. Why all of them are different selectively permeable in terms of what they allow, what they don't allow, is because of the composition of these phospholipids. The composition of the phospholipid gives those membrane their characteristics. I think at this point I want to be getting some questions. I want to be getting some questions. So if you take the heart muscle and you study the phospholipid composition, it will be different from that of the kidney. It will also be different from that of the liver and other different organs in the biological system. And because of their difference in composition of the phospholipid, that is what gives them their characteristics of what they allow and what they don't allow. So you can see, like I told you, I've explained this kink nature that you're seeing here. The kink nature is to make sure that the membrane are not tightly packed. So just like when you have someone that has a knock knee, and you expect maybe let's assume you bring 10 persons with straight leg and 10 persons with knock knee. Now you want them to do a match pass. Which one do you think will compact very well? Of course, the one with straight leg. The one with knock knee will disperse. And those are the characteristics of a liquid. We say, if we want to differentiate between liquid, gas, and solid, we say for gas are entirely loosely, they are loose, while the liquid are loosely packed, while gas are tightly packed. So liquid that are loosely packed is because of the nature of how the molecules do not aggregate. If the molecules aggregate finely, they will form solid. But if they aggregate loosely, they will form a liquid. That is why if you're buying oil in the market today, you will see some people selling oil that is already sleeping. That's what we call it, oil have congealed. We say this oil is sleeping. I will not want to buy it because we have been told that the oil that is sleeping is a bad oil. Why is the oil sleeping? Because the oil is made up of saturated fatty acid. And that saturated fatty acid will make sure that the oil do not, because of their nature, they can compact very well. When they compact very well, they form solid at room temperature. And that's one of the defining characteristics between fat and oil. So now you can see the nature of the phospholipid in our on the system. What we have here is a choline, is a phosphatidylcholine choline. So this head is what is interacting with the water, while this tail is what is forming the hydrophobic core of the plasma membrane. Can others hear me? Chikamso is saying she can't hear me. He or she, I don't know, can't hear me. Please, if you can hear me, make a comment. If you can hear me, make a comment. Okay. So now, okay, there was something that happened, right? I was questioning why they sell oil in a clear, but more especially those oil that they told us is good for the heart. That this one is good for the heart. It will reduce cardiovascular disease or cardiovascular issues. But the oil has been sold in a clear container. And I was like, in biochemistry, we were taught that the double bond is susceptible to oxidation. So if there is oxidation in double bond, it will make the oil, to spoil the oil, make the oil become rancid, which will defeat the purpose of telling us that this oil is made up of polyunsaturated fatty acid, which is good for the heart. Why not store the oil? Why not sell the oil in an amber bottle? Because amber bottles are bottles that are known to prevent light penetration. So if there is no light penetration, there will be no photo oxidation. So I was querying it, just like somebody telling you this is cholesterol-free oil. No, you see where is the plant oil. Why you're not supposed to have cholesterol in plants? Moreover, cholesterol is also very good for the system. You have a very good skin. Is cholesterol. Cholesterol contributes to the fluidity of the membrane. So we'll end at this point for now. We'll see next time. I believe we'll just call this one for the year. We'll meet in January. While we're throwing some short videos on question and answers. So please do well to follow and click the notification bell for more updates. Thank you.